We are starting our first day of electrochemistry, and as part of that, we're going to start with something that you guys are probably already familiar with, and that is assigning oxidation numbers. Now, oxidation numbers really just means charges. And here, in this case, we're going to be talking about charges on individual elements. We're not going to be looking at the entire compound. We're going to be thinking about each individual element and the oxidation number or charge on it. So these rules, I know it might look daunting when you first peek at these, but you will have them memorized just because it's so simple and easy. They will make sense to you. The first one just says the oxidation number of any free element is 0. Well, that makes sense. It's neutral. So if you have a free element, maybe you have iron, or maybe the silver ring that you're wearing, silver, or oxygen that's in the air, chlorine, whatever it might be. Those are all considered free elements, and the oxidation number, the charge on those are all 0. They do not have a charge associated with them. Well, next one. The oxidation number of a monatomic ion is the same as the charge shown on the ion. Couldn't get much easier than that. If you had something like Fe plus 2, well, that's just saying the charge of that, the oxidation number of Fe plus 2 is plus 2. It's pretty much spelled out for you. It tells you what it is. Number 3, the oxidation number of hydrogen is almost always going to be plus 1. Now, this is the case for most of the times that we see hydrogen. Maybe it's an acid like hydrochloric acid. Yep, it's going to be plus 1. Or as water, you've got that hydrogen there. You've got a plus 1 charge for it. Or maybe you see it in an organic compound like methane. Well, that hydrogen is going to be a plus 1. So you're almost always going to see it as a plus 1. There is the rare situation when it acts like a hydride. And just by that word, looking at what that word sounds like it must mean, you guys can probably figure that out. It's got that "ide" ending, which means it's acting like a nonmetal. In other words, it's acting like an anion. So in this case, you would see when hydrogen's a hydride, you would see it combined with a cation. So you'd have a cation and then hydrogen as your anion. And in that case, it would be a -1 charge. All right, number 4. Oxidation number of oxygen. Well, you know this. You'd look at the periodic table and say, yeah, oxygen is a -2 charge. Again, that is going to be in nearly all of the cases. But occasionally you get a peroxide in there. And if you remember, if you look at your polyatomic ion sheets, peroxides are just O2 with a -2 charge. That is on your polyatomic ion sheet, O2 with a -2 charge, which means each of those individual oxygens, because we're always talking about individual elements, each of those has that -1 charge on it. So there's a special case. Number 5, this is going to be used to help us do some calculations. But again, this makes sense. The oxidation numbers of all species in a particle must add up to the charge on that particle. Well, what that means is that if you have just a compound, a neutral compound, it's going to add up to be 0. If it's not a neutral compound, if it's a polyatomic ion, then you know what the charge is that it's going to add up to. So we're going to use number 5 to help us do some calculations and determine some of these that are not part of this list of rules. And then number 6, oxidation numbers of group 1A, in other words, your alkali metals. You know this, alkali metals, plus 1. Oxidation numbers of group 2, alkaline earth metals. They're always going to be a plus 2. And then your group 3, really what we're looking at is aluminum is always going to be a plus 3. That's the main one that we want to think about, but we've got some others in there that could be plus 3. Okay, so with that said, we can go through and do some calculations. Now, there is no formal way on how this should be written, but what you're going to see me do is that I'm going to write my oxidation numbers on top of my element symbols, and I'm going to put a circle around them. Then underneath, I'm going to go ahead and do some scratch work, because we're just going to be, you're ultimately going to get to the point to where you don't really have to write this down. But in this process of learning, I'm going to do some scratch work underneath. All right, so the first one, NO2. out of those, N and O, which one do you know the charge of, the oxidation? Oh, so you know oxygen is going to be -2. That is the oxidation number for oxygen. But you got 2 of them. So here's my scratch work. That gives me a total charge on my oxygen of -4. Well, I know that when I add up my nitrogen's total charge and my oxygen's total charge, what is it going to equal? 0. That goes back to rule number 5, that the oxidation number is going to add up to the charge on that particle. Well, it's just a neutral compound. It's NO2. So it's going to add up to 0 in this case, meaning nitrogen would have to be a +4. Well, you've only got 1 nitrogen, so that 1 nitrogen has to be a +4. So I know that you're probably looking at this right now and looking at the periodic table and scratching your head and thinking to yourself, wait a minute, I could have sworn nitrogen was a -3. And the answer to that is, yeah, it usually is. That's a very common oxidation number for nitrogen, especially when it acts as the anion in an ionic compound. It's going to be a -3 charge. But this is not an ionic compound. It happens to be a covalent substance where you've got these 2 nonmetals. It still does have an oxidation number associated with it. Okay, and I got this question earlier too. Just received a question asking, how do we know that this is not peroxide? So remember, and I know it might look a little deceiving because we think peroxide's O2 with that -2 charge, but remember peroxide is a polyatomic ion. It's acting like an anion, so that would mean it would have to be combined with a cation. You would have to have a positive charge of a metal. Right? This would have to be a metal from the periodic table, and nitrogen is not a metal. Yes, it's got this positive oxidation number in this case, but it is not a metal. So because of that, it cannot be peroxide. Good question. Okay, next one. Let me just point out that it's NO3, and then there's that little minus. Lots of times you'll see if it's a -1, you just see a minus, or if it's a +1, you just see a plus. But that is a -1 is what that's implying. So again, just like last time, we know the charge of oxygen. It's -2. That's our oxidation number, giving us a total charge of -6. Now, when we add up the total charges of all of those elements, what does it have to equal for this? -1, because of this guy. So because it's that negative charge. So typically it's going to be 0 for neutral compounds, but if it happens to be a polyatomic ion, then we would have it add up to that charge. So it's going to add up to be -1, so that means that nitrogen has to be +5. Okay, so math isn't too hard here. Just have to make sure you go through and grab the right numbers. All right, next one we have potassium permanganate. So a couple of these that I know the oxidation number of. Name one of them. Oxygen. What's another one? Potassium. So we know both of those. Potassium, look at your rule there. We see it's a +1. Oxygen we know is a -2. So when we start adding these up, the total charge on your potassium is +1. Manganese is the one in question. That's what we're going to figure out. In fact, there's a whole bunch of different oxidation numbers for manganese, and it's kind of neat because they show different colors based upon the different oxidation numbers for them. And then our oxygen is going to be a total of -8. All of that together has to equal, I look, there's no charge. It's just going to be a neutral compound, so a 0 for our potassium permanganate. So that means our oxidation number for manganese is what? 7. There we go. All right, we come over here to our dichromate ion. Again, oxygen, -2, giving me a total of -14. When I add this up, what's it going to equal? -2. So that means my total charge has to be +12 for my chromium. So is that my oxidation number? No, because I've got 2 of them. So each one has to be +6. All right. Next one, we've got NaH. fact, think to yourself, how would you even name this? Anybody want to take a shot at trying to name this guy? What do you think? Sodium hydride, exactly. So sodium hydride, we've got this positive ion, this cation, and this negative ion, this anion. So in this case, actually both of these we know. Lots of times we have to go through a calculation, but I know because of this, this means my alkali metal is +1, my hydride is -1. So that was that exception that we saw in that list of rules. All right, last example here. I go through, I know my oxygen is -2. What else do you want to say? Hydrogen, +1. For all of those hydrogens, they're all +1s. There are no hydrides. It's not a metal and a non-metal. And that means we're going to have to end up figuring out our carbons. So if I add up all of my hydrogens, I see I get a total of +4. I add up my oxygens, I see I get a total of -4. Well, this whole compound has to have a charge of 0, meaning carbon's charge is 0. So the oxidation number for carbon is 0. Yes, it's possible to have 0 for an oxidation number. Okay, feeling good with this so far? Good. All right, so that's going to be important for us to be able to figure out some information about the type of reactions that we have. And we're going to talk about something known as oxidation and reduction. So to give you a little bit of background here, oxidation was originally meant to be the combination of some sort of element, typically a metal, with oxygen. So for example, you might have something like this silver fork that combines with oxygen and you get a silver oxide, in other words, tarnish. Or here we have this iron that combines with oxygen to get an iron oxide, also known as rust. Or here we have copper that combines with oxygen to get a copper oxide, also known as that patina that you see on copper. So all of that is the process of oxidation. These have all been oxidized. The opposite would be reduction. And the easiest way to think about this is these nice metal ores that are found, that they might be something, it might be like a copper sulfide or a copper oxide, some sort of combination, some sort of compound that contains a metal in it, and it can be reduced to that pure metal. In this case, it happens to be copper. So this process has taken place for thousands and thousands of years. This reduction process was used on the Greek island of Cyprus, which was then eventually changed to Cyprium, which was then changed to cuprum, and which we now know it as copper. But if you think about the Greek roots to our element symbols, we can see that copper up there, it's that Cu, and that comes from cuprum. So if you think about iron, for example, we have that ferric or ferrous. Well, here we can have cupric or cuprous. We didn't learn that naming system this year, but that's where the symbols come from, is that root. Okay, so now what this means, let's think about what these reactions are like when we have oxidation and reduction. So first of all, let's look at this term right here. We're going to refer to this process as redox because it's not possible to have one of these types of reactions without the other. So these two processes must occur together. You cannot have reduction without oxidation and vice versa. They always have to occur together, and that's where the term redox comes from, reduction and oxidation. So these, we're going to be looking at redox reactions. If we're going to talk about oxidation in terms of electrons, what's taking place is that electrons are being lost. So oxidation is the loss of electrons. The loss of electrons. Whereas, let's just jump down to reduction. You guys can probably guess. It's going to be the opposite. It is the gain of electrons. Gain of electrons. Which might be a good time for us to look at this pretty picture that we have on top. That is a picture of an oil rig. And why do we care? Because that's a nice little way for us to remember this. That oxidation is loss of electrons. Oxidation is loss. Reduction is gain of electrons. So if you remember oil rig, you can remember what's going on with those electrons. Oxidation is loss, reduction is gain of electrons. Now here's the tricky part for some people, is that we're talking about electrons, and if you think about the charge of electrons, they're negatively charged. So we're talking about losing negative particles or gaining negative particles. And so it feels a little bit different to people. It feels like it's backwards. But if you're losing negative particles, what happens to your charge? Becomes what? More positive. So oxidation becomes more positively charged, whereas reduction, where you're gaining electrons, you're gaining negative particles, it becomes more negatively charged. And in both of these cases, just like when we talked about oxidation numbers, we're always going to be talking about the individual element. It's always referring to the individual element, not a compound, but the individual element. All right, we're going to apply this now. We can go through and write some half reactions for these redox reactions. So we can just show one side of that process, one process, the reduction or the oxidation process of those reactions. And in order to do that, we have to also show those electrons and what's happening to that charge. So we can start with this first one. It's almost spelled out for us. It says Ca becomes Ca plus 2. So all we have to do is say, yeah, Ca becomes Ca plus 2. Pretty simple. But there's something a little bit wrong with that. If we think about our oxidation numbers, what's your oxidation number over here on the left-hand side? 0. On the right-hand side? Plus 2. So we need that to be balanced in charge. And the only way we can balance it is by adding electrons. So if we want to add those negative particles to balance this, which side of our reaction do we have to add them to? To the which side? The right side? The right side? So here we're going to add our negative particles to the right-hand side. And notice I added 2 of them because here we had a 0 oxidation number or charge. Here we had a plus 2. So by adding 2 negative particles, we now have a charge of 0 on the right-hand side. Okay, let's do another one just like that before we talk about that. Okay, sulfur becomes, the sulfur atom becomes the sulfide ion. So again, thinking about only being able to add negative particles. Which side do you want to add it to? The left side. And I think you guys can all look at that and say, yeah, you've got to add 2 of them. So now you have a negative 2 on the left-hand side and a negative 2 on the right-hand side. Notice that the charge doesn't have to be equal to 0. It just has to be equal on each side. So up top, I had 0 charge on each side. Here, I've got a negative 2 charge on each side. Okay, so now that we've got that done, the great thing about seeing these half reactions is that if we want to think back about what we just said, and I know it went away, but we want to think about the loss and the gain of electrons, well, which one of these, calcium, if we look at calcium and calcium plus 2, what's going on here? Are we gaining or are we losing electrons? Losing. We see them on the right-hand side. That is a loss of electrons, also known as oxidation. If I look at my sulfur half reaction, I see that this is a gain of electrons, also known as reduction. So by seeing your half reaction, it really clearly spells it out for you as to whether you're gaining or losing electrons, so whether it's reduction or oxidation. Okay, next couple. Here we have aluminum plus 3 goes to aluminum. Where you want to add your electrons? How many? There we go. Hey, is that oxidation or reduction? Reduction. Next one. This one's a little trickier. I'm going to take my bromide ion and go to bromine. Now, do you see anything here that you might want to do before dealing with your electrons? Balance it. So I look and I see I've got two bromines, two BRs on the right hand side. So I have to have two BR minus ones on the left hand side. We really talk a lot more about balancing tomorrow, but finishing up with this, we would then say in order to get this balanced, you've got a -2 on the left, a 0 on the right. So we have to add 2 electrons to the right hand side. And in this case, this happens to be oxidation. Okay, so now let's look at this example where we have a reaction spelled out for us and we want to figure out what's being oxidized and what's being reduced. So I'm going to write my oxidation numbers on top of these elements. Remember, oxidation numbers are for individual elements, not the whole compound. And I'm not going to do my scratch work anymore. I'm just going to think about it, but I'm not going to write it down. So with my methane here, what do you know the charge of, your oxidation number of? Hydrogen. It's +1. Do a little math in your head. What does that mean carbon has to be? -4. Okay, tricky one. Oxygen, what's oxidation number? What is it? 0. I heard it. There we go. It's real tempting to go, yeah, oxygen's going to be a -2, but here it's a free element, remember. So it's not in a compound. You don't think about the charge that way. It's a free element, so it's going to be 0. That was our first rule that we saw. Okay, carbon dioxide. Now you can look at that and say oxygen is -2. Therefore, your carbon must be what? +4. Okay, now we come over to our water. You happen to know both of those, your hydrogens and your oxygens. There's nothing you really have to calculate. You know your hydrogen's +1, your oxygen is -2 in that case. So then you have to look at this and ask yourself, what is changing? Remember, you can't have reduction without oxidation or oxidation without reduction. So I look at this and I say carbon. Yeah, my carbon's changing. Carbon goes from -4 to +4. So we see that as a change. Next one I come across is my hydrogen. +1, +1, no changes going on. It stays the same on each side. So there is no change taking place. Oxygen, yeah, there's a change taking place. Goes from 0 on the left-hand side to -2 on the right-hand side. So those are the changes that we note. Now let's think about what's being oxidized and what's being reduced. And this, again, this is where it gets tricky for people, I think, because electrons are negatively charged. So you kind of have to factor that into your thinking. If carbon goes from, I thought I unplugged, sorry. If carbon goes from -4 to +4, did it gain or lose negative particles? It lost negative particles, therefore becoming more positive. So if it loses negative particles, what's that called? Oxidation. I'm going to make myself that little note here. Let's just double check, because we can't have this be oxidation as well, otherwise we made a mistake. Oxygen goes from 0 to -2. Did it gain or lose negative particles? Gained. It gained them. So that's got to be reduction, so we can fill that in. Element oxidized is our carbon. Element reduced is our oxygen. I'm going to write that correctly for how you would write that element. Okay, so what we're going to see tomorrow, before we flip our page, I'm not going to spend too much time on this other than to show you that we could easily write half reactions for these and say CH4 goes to CO2, 2O2 goes to 2H2O, and we could go through some processes of balancing these, and that's what we're going to do tomorrow. And by doing that, getting it down to our half reactions, and I know these half reactions look a little bit more complicated, but by getting it down to that, again, we would be able to see just by looking at where those electrons are located, which one is oxidized and which one's reduced. So what ends up happening is we have our electrons over here on this side, and we would have our electrons on this side for our oxygen, but we'll talk more about that tomorrow. Okay, that now takes us to the second part of this, and this is calculating EMF, which stands for electromotive force. And really, when we talk about electromotive force, another term that we could use is voltage. Voltage. And really all this does is measure the push or the pull on the electrons within that half reaction. So it's going to give us a feel for the energy that's going to be involved in this reaction. And it's going to be measured in volts. One of the things that you have in front of you, and my class, I'm in paper saving mode, so it's on the back of your first homework. So if you flip to the back, you'll see this chart. Make sure you hold on to this because, you know, it's on the website, but it's just something you're going to refer to quite a bit. So notice that this is called a standard reduction potential table. Even if it didn't have that title, how do you know that that's what it is? What else do you notice about it? How could you tell? Because why? Well, not just what do we see about? Yeah, the electrons, we're adding them in every single case. So they're always on that left-hand side, we're adding them. In other words, that's reduction. Sure, we could make a table known as a standard oxidation potential table. It would be redundant. It would just show all of this information as well, but it would be reversed. We're going to end up using this, and this is what we're going to see here. We can calculate our half-cell voltage potentials. And what this tells us is the tendency of an atom or an ion to gain electrons, and it can be measured with a voltmeter. So eventually we'll go through a process in lab where we're going through and calculating this, measuring it with a voltmeter. Remember, the symbols that we're going to use is our volts. When you look at your reduction potential table, notice right here is your 0 mark. So these guys that are more negatively charged, they are more easily oxidized. These guys that are positively charged are more easily reduced, is what we end up noticing. So that 0 mark is just a standard that was arbitrarily chosen and set at 0. So we're going to compare everything to that. If it gains electrons more easily, then it's going to have a positive reduction, a positive voltage, because that's the reduction that we're looking at. And if it gains less easily, then it's going to have a negative voltage. Okay, and basically we're going to now, we'll spend a day talking about something known as voltaic cells, but does anybody know another name for a voltaic cell? Battery. Okay. So we'll spend some time talking about this, and we'll do a lab on this after spring break. But a voltaic cell is just made up of a spontaneous redox reaction. Makes sense that if you're going to make a battery, you want it to be some sort of chemical reaction that happens on its own. It is spontaneous. So that's what a voltaic cell is. A redox reaction is spontaneous if it has a positive total voltage. And when we go through this, you're going to be looking at your reduction potential tables. And again, you noticed on your reduction potential table that everything's written as reduction. So we also notice on here that we've got this information right up top. It's just showing us that these standard conditions apply. This is the voltage measurements at these standard conditions. Doesn't come into play for a few days. When we start talking about the Nernst equation, that's when we're going to change those things up. But just notice those are our standard conditions. And we also know that since these are all written as reduction, if we want to find the oxidation potential, well, you have to flip it to make it oxidation. Well, if you flip it, you also have to change the sign for your voltage. Okay, so here we go again. We're going to go through calculating these. These are our rules. You're going to break it into half reactions. You're going to look up your reductions. Remember about the flipping of your oxidation. You just add those voltages together, and it is considered spontaneous if your voltage is equal to a positive value. It is considered non-spontaneous if your voltage is equal to a negative value. That you might, I know it's written right here, but sometimes seeing that handwritten is a little bit, catches your eye a little bit better. Okay, first example, which is pretty much spelled out for us already. We're given this reaction. And it happens to be in the form of a net ionic equation. I know you guys like thinking about those things again. So we've got this net ionic equation given to us. We can easily break that down to those two half reactions, your cobalt solid going to your cobalt plus 2 ions, and then also your iron plus 3 ions going to your iron plus 2 ions. So those two half reactions have been done for us. Then we had to add our electrons appropriately to be able to get those charges to balance on each side. So notice you have a charge of 0 for your cobalt on the left, and now a charge of 0 on the right. Here you have a charge of plus 2 for your iron and a charge of plus 2 for your iron. So those are all good. So now, since we see this, we see losing of electrons for our cobalt. Losing of electrons. What's that known as? What's that term? Losing of electrons. Oxidation. Good. And I want that to come really quickly to you guys. So that's going to be one of those things you think about all the time. So our iron, we're gaining those electrons, so that's reduction. So when you look at your reduction potential table, this guy right here is going to be written exactly the way you see it. You look it up and you see, yeah, there it is, that voltage of 0.771. And it's spelled out exactly like that. But when you look up your cobalt, you can look all day long, but you won't see it written like this. Instead, it's going to look flipped. You're going to see the CO plus 2 electrons yields your CO. So in order to write this down and flip it to make it be that oxidation, you also had to flip the sign. So it was a negative value on your reduction potential table. You flip it and make it positive because you've changed it from reduction to oxidation, so you've changed the sign as well. So when we add this up, we see that we get, I guess I can add this up, 1.048 volts. So what that means is, yes, this is a spontaneous reaction. This will occur. Now, the next thing I want to mention here might not make a lot of sense to you guys yet, but it'll make more sense tomorrow. The note being, do not multiply your voltage by any factor in the half reaction, even though you might need to balance your electron loss. So that's going to come into play tomorrow when we start balancing these half reactions. And then the tendency is that people are going to want to also multiply these values by a number, and this, put a star by it, and then that way you can look at this later and remind yourself once we start doing this type of information. And I'll remind you again tomorrow. But you do not multiply that. It is as you see it. Okay, now we get to our examples. And I wish this wasn't our first example, but it is, so we'll stick with it. We've got hydrogen and chlorine, so I'm just going to break it down to my two half reactions. So H2 goes to 2H plus 1. Notice I'm not going to write my phases. I can live without those being written as half reactions. And then my Cl2 goes to 2Cl minus 1. So I've broken it down into those two half reactions. Now I can go through and add my electrons to balance the charge. For my hydrogen, where do I need to add my electrons? Which side? The right side. And you know how many? I bet you do. 2 electrons. Okay. You're hoping that it works out this way, because if you had to add to the right side for your chlorine, you made a mistake somewhere. So in this case, we look and, yeah, your electrons need to be added to the left, because remember, you cannot have reduction without oxidation, and vice versa. So by looking at this, which one is being reduced? Chlorine is being reduced, meaning you are going to be able to read that voltage for chlorine exactly the way you see it on that table. Let me give myself a little bit more space here. I'll write it right here. This is reduction for this guy, meaning this is oxidation, losing electrons. So now when I look this up on my reduction potential sheet, my chlorine, yes, I see it right here as 1.358, exactly the way I see it on my reduction potential sheet, because this is reduction, and that's a positive value. And the reason I didn't want this one to be the first one is because my hydrogen, well, hydrogen's 0, but because it's oxidation, we had to flip the reaction, the half reaction, meaning we also changed the sign on it. Well, it's 0, so there's really not anything we can do there. So when we add this up, we get a positive value, meaning is this going to happen or not? Yeah, it will. It is spontaneous because it's a positive voltage. Actually, I didn't write that right. There we go. It's a positive voltage. Okay, so next one. Here it says that we've got nickel and iron, so I'm going to break this up into our half reactions. And hopefully you guys notice that I'm just keeping the things in as reactants remain as reactants, things that are products remain as products. All right, so that's our half reactions. Pretty quickly, you're probably able to throw in those electrons where you need to. Then you're looking at this and going, aha, yeah, this guy right here, that's oxidation. There's a loss of electrons. Here is a gain of electrons. So now when we look this up, and be careful because some of these, like your iron, for example, has a whole bunch of different oxidation numbers on there. So you spend some time looking for this guy, and it ends up being right down here. And I'm looking at my iron first because that's the reduction half. So I see that iron is right here. That's that +2 going to its element. So it's negative 0.440. Negative 0.440. And I do the same thing for my nickel. It's a nickel with a +2, but I'm not going to find it like that. Instead, I see it as a reduction half right up here. So that means instead of it being negative 0.257, I need it to be positive. I have to flip. Since I flipped my half reaction, I also have to flip my sign. So now when we add this up, I can't do this kind of math in my head. It's negative 1.8 something or another. You guys can do that. Anybody get an answer? 0.3? Yeah? Is that what you said? No? Somewhere in there. I'm not going to take the time to plug that into my calculator. I've got too many things in my hands right now. But we would get a negative value. So that negative value, that means not spontaneous. This would make a pitiful battery. You would never want to make a battery like this because it wouldn't do anything for you. It is non-spontaneous. All right, next one. Here we have aluminum going to Al plus 3, and we have Fe plus 2 going to Fe. Again, I'm hoping you guys are getting kind of quick at this and going, yeah, I'm going to add 3 electrons here and 2 electrons here. This is oxidation. This is reduction. You look up your reduction half, you'll find it just the way you see it. And we see right here it's that negative 0.440. But for our oxidation half, oops, your aluminum, it's not oxidation here, it's reduction. So instead of negative 1.676, it has to be flipped and become positive 1.676. All right, so we get a positive value, meaning yes, this would make a fabulous battery. And the voltage, it's going to be volts or units. Okay, last one I want to spend a little bit more time on. And here, I know you guys probably ponder this at home all the time. You want to make that big old vat of aluminum chloride, and you're asking yourself, can I use the iron spoon, or should I maybe use a wooden spoon instead? Is a reaction going to occur if I try and create my vat of aluminum chloride with an iron spoon? How many times have you asked yourself that? Multiple times, yeah. Okay, so I'm going to spell out everything in this. I'm going to start by writing a molecular equation. So I see that I've got my iron spoon, and I'm going to throw in some phase notation also. It's a solid piece of iron, and I'm adding it to my 1 molar aluminum chloride solution. It is a solution. It's aqueous. You could prove it to yourself and look at your solubility rules, but it is aqueous. So when this forms, it is going to form an iron chloride. Well, which iron chloride? I bet right now, in your head, you're thinking, as Stan fell, huge cups cracked. Fell. So it's that higher charge, iron 3. It is aqueous. Plus your aluminum, which is solid. So if you were to write out the molecular equation, that's what you would get. Then you could go through your whole net ionic process, and you would see chloride is just a spectator. So when you rewrite this as a net ionic, and I'm not going to take the time to balance it, that's not really important for this, but when I write this as a net ionic, I get iron that is solid plus aluminum ions that are aqueous. It goes to iron plus 3 ions that are aqueous plus aluminum solid. Now it becomes just a simple little one that we've done like the last 3 examples. But getting it to this point, you just have to read through and think to yourself, yeah, that chloride's not important in this example. It's going to cancel out. So now when we go through this, I'm going to break this down into my 2 half reactions. So I have my Fe going to Fe plus 3, and I have my Al plus 3 going to Al. Those are my 2 half reactions. I can easily look at that and figure out where to throw my electrons, right? You guys know what to do there? 3 electrons there, 3 electrons there. Oh, that means this guy's being oxidized, this guy's being reduced. Then we just go and we peek at our reduction potential table. Reduction is your aluminum. So your aluminum, you're going to keep it just the way you see it. Whereas your iron, and be careful, make sure you grab that iron plus 3. It's an oxidation half. So because of that, we have to flip the sign. So it becomes, instead of being a negative 0.40, it is now a positive 0.040. So this means that when we add this up, I think I'm doing this right. That's a tough math right there. It is a negative value. So I can feel at peace knowing that yes, this is not spontaneous. When I create this big old vat of aluminum chloride, I am not going to have to worry about my metal spoon interfering with my aluminum chloride. It will not react. It will not take place. Now take a second to look at that and ask yourself, is there another way for you to have figured this type of information out? Something that you did many units ago. Think about that for a second. I'm going to pause this and let them really think about it. Such a bright group. They figured it out. So they remember that, yeah, they looked at their activity series many units ago. They looked and they said, hey, is iron really strong enough and manly enough to come in and kick aluminum out of the dance? And the answer is no, he's not. It would not occur. So this reaction, you would look at your activity series and this reaction would not occur. Aluminum is stronger than iron, so therefore or more active than iron. So that's just another way. You guys have come full circle and you've seen the same type of information in two different ways, through an activity series or thinking about voltages and reduction potentials. All right, that should do it.